Hey guys, welcome back. I'm going to talk a little bit about kinetic energy and conservative and non-conservative forces. So kinetic energy is going to be energy of motion. So anything that's moving and has mass will have kinetic energy. This is given by capital K equals 1/2 mv squared. Because the v is squared, you can never have negative kinetic energy. But as we'll see, and we saw in the potential energy, it's going to dwarf in size to universal potential energy. The units for this is also going to be joules. So what is the energy associated with a 0.052 kilogram B that's traveling at 5 meters per second? First, I'm going to put down my formula. Again, that's capital K. We don't want to confuse it with lowercase k in this section. And so this is going to be 1/2. We have a mass of 0.052 kilograms, and then a velocity of 5 meters per second squared. Again, I need to retrieve a calculator. Morning. So this is going to be 0.65 joules. So the idea is that this B has a certain amount of energy, and that energy could do work. Whether we attached a small block to this and had the B drag it, or had it lift something up, it would be able to do an amount of work. All right, the second part of this short video is going to be conservative and non-conservative forces. So all of these are going to be scalars, and we're going to be able to change things from one to the other, find out how much work was done, find out how much energy there is, and how that changes. But before we do, we need to talk about conservative and non-conservative forces. So there's going to be forces where it's going to be easy for us to get the energy back. When we put the energy in a certain place, you can get it all back, and there's no problem with it. There's going to be other places that if you put the energy there, it's going to be difficult or nearly impossible to get the energy back. The ones where you can get the energy back easily are called conservative forces. So an electric field, gravitational field, those would produce conservative forces. Friction, air resistance would be non-conservative forces. That energy goes to heating up the individual molecules you're rubbing against, and it's really hard to get that back. So our conservative ones are going to be gravitational, electric, and elastic. I didn't mention, but you put the energy in a spring, it's easy to get most of it or all of it back. Non-conservative ones are going to be friction, air resistance, tension in a cord, motor or rocket propulsion, push or pull by a person. So you can imagine if you're exerting a certain amount of force and it's going into the ground is heating up, we can't get that back. Which is one of the reasons why hybrid cars are more efficient than gas cars, is that typically in a regular car, your brake pads are heating up, and it's the friction that actually stops it. And all that heat is wasted energy. Well, in a hybrid car, they use that energy that used to be to friction to actually charge batteries. And so instead of doing that, you're using a generator to charge batteries, and you can get that energy back, and you can make your vehicle more efficient. Potential energy can only be described for conservative forces. So we're going to talk about whether the work is done by conservative or non-conservative forces, whether we can get the energy back or whether we can't get the energy back. If we can't get the energy back, we know that the energy change is equal to the work done by that. So the energy didn't disappear. It wasn't destroyed. We know where it is. We just can't easily get it back.